So this is your homework tonight is page 881, number 45, 47, 51, 53, and 55. So we use terms in this chapter, which is chapter 18. And this is thermo. And we're going to use terms like spontaneous, and when we use this, it means that it doesn't need outside input to go. The reaction is spontaneous. It doesn't need outside input. Or non-spontaneous. And if a reaction is non-spontaneous, it needs outside input. Okay, so one of the main concepts here is something called entropy. And entropy is as delta S. Entropy is the randomness in a system. So I tend to think of this, it's called the randomness in a system. I tend to think of this as chaos. So in general, the world, the universe seeks more chaos. So think about the Big Bang. Started as a teeny dot, continues to expand and seek more chaos. Think about a herd of horses. When you open the gate, the horses go out and they move further apart. They expand, they seek more chaos. The world seeks more chaos, all right? And so, therefore, in general, delta S of the universe is greater than 0. It is positive, right? We say that the delta S final minus delta S initial is equal to, S final minus S initial is equal to delta S. Yeah, that makes sense, right? And a positive delta S is favored. And the reason is because increased chaos is what the universe wants. The universe wants less organization. That is what the universe wants. So, positive delta S would include melting. So going from a solid to a liquid, where greater energy is input and the particles are going from like dot, 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 dot to a little bit more chaos, right? Or vaporizing, more chaos. We like that. Vaporizing is better. Or, and this is important, dissociation into aqueous. That is important. That is positive delta S. Gas has greater delta S than liquid. Liquid, greater delta S than solid. Greater moles has greater disorganization than less moles, right? So if a a reaction goes from 4 moles to 6 moles, that is a delta S, greater disorganization. The delta S of the universe is equal to the delta S of the system, which is the reaction, plus the delta S of the surroundings. So if the system increases in chaos and the surroundings increases in chaos, then that means the universe increased in chaos, and that's good. All right? So let's look at an example real fast. So we have C3H8 gas plus 5O2, so this is a combustion. 3CO2 gas plus 4H2O gas. Okay, and the delta H for the reaction is equal to negative 2044 kilojoules. So first, 1, calculate the entropy in the surroundings at 25 degrees Celsius. So, first, the equation for this is delta S for the surroundings is equal to negative delta H over the temperature. So this is super easy. We're just going to plug this in, and we're going to say delta S for the surroundings is equal to negative delta H, which is going to be negative 2044 kilojoules over temperature, which is 25 plus 273 Kelvin. And that gives us kilojoules per Kelvin, but we like delta S to be in joules per Kelvin. All right, so that gives us 6.86 kilojoules Kelvin, and then we're going to convert and that is our delta S surroundings. So this is the change in the surroundings due to the, I want to be clear, due to the change in the chaos of the entropy, due to the change in the entropy of the system. So this is my system. Because I know the change in the energy of the system, I can calculate the change in the chaos, the entropy of the surroundings. Because I can calculate the change in the energy of the system. So the change in the energy of the surroundings, I can calculate right here. All right? So that's that. Now I can determine the sign of the energy of the system. So number 2, determine the sign of the end of the system. Determine the sign of the entropy of the system. So the sign of the entropy of the system is positive. The reason is, so positive, and the reason is I'm going from 6 moles of gas to 7 moles of gas. So that means that my entropy of the system is getting greater. 6 moles of gas to 7 moles of gas. The system is the reaction. Okay? So 6 moles of gas to 7 moles of gas. Okay. Okay. All right. So the last step of this, number 3, the last problem here is going to be to determine the sign of entropy. Okay, determine the sign of entropy for the universe. Okay, now remember, delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And since we know that delta S of the system is positive and delta S of the surroundings is positive from previous questions, here and here, we know they're both positive, so that means that the delta S of the universe must be positive. So that means that the reaction must be spontaneous. And we know this because up here it says that any reaction would be spontaneous if it's positive, right? Okay, so let's add some things in here that we know. We now know that the units for entropy are joules per Kelvin. We know that, so let's add that in. Is it acceptable to make kilojoules? Yes. We could say kilojoules per Kelvin, but I'm telling you that they're going to be coming to you on the test in joules per Kelvin, all right? Just so you know. The next thing is that if it's positive here, if it's positive, hang on, all right, so delta S is favored, and so because of that, we're going to say that this makes it, if delta S is positive, we're going to say that this makes it spontaneous. All right? So that's why down here, we said that down here, when we determined the sign of the universe, right, that delta S, the sign of the universe, is positive, we said that makes this reaction spontaneous. Okay, next we're going to look at Gibbs free energy. So Gibbs free energy, this is the big concept, the big one, all right, Gibbs free energy. So the formula for this is delta G equals delta H minus T delta S. And so try to remember this. I think about this. Go home to sleep, because I will always remember that. Go home to sleep. You can remember it however you want, but that's how I remember it. Okay, so Gibbs free energy is the delta G Gibbs free energy is a determination of spontaneity or non-spontaneous reactions, where if delta G is less than 0, negative, then this is a spontaneous reaction. Again, no input needed, no external input needed. If delta G is greater than 0, positive, then it's non-spontaneous. Input needed. All right, if delta G is equal to 0, the reaction is at equilibrium and will not move in either direction. Okay, so now we have this equation that has delta H and delta S in it and T, and we want to know, without doing every calculation, the question is, can we determine whether delta G is going to be positive or negative? Because that's going to tell us whether the reaction will be spontaneous or not. So we can, and the reason that we can is because if we have delta G is equal to delta H minus T delta S. Remember that T is always positive because T is in Kelvin. And so because of that, T in Kelvin is always positive. So you can figure out whether delta G is going to be positive or negative. So here we go. Delta H, delta S, T, and then delta G. So the questions on the AP exam look like this. If delta H is positive and delta S is positive, and delta T is very low, will delta G be positive or negative? And so you need to know that delta G is positive. Why? Well, if delta H is positive and delta S is positive, then that means that positive, with the delta S being positive, then you're going to be subtracting another number, and so if delta T is very low, then the delta G is going to be positive. But if the delta T is very high, then you're going to be subtracting, it's going to be negative because you're going to have a positive number and you're going to be subtracting a high positive number. So then your delta G is going to be negative, right? Okay, what if your delta H is positive, your delta S is negative? Well, now you're going to be adding a number, and so for all delta T's, which are all T's which are positive, you're going to be adding a number to it, and so your delta G is always going to be positive, and there's no way out of that. You can't handle, there's nothing you can do about it. Next, your negative, which means non-spontaneous, right? So this is going to be non-spontaneous, this is going to be spontaneous, this is going to be non-spontaneous. Next, if your delta H is negative and your delta S is positive, so negative and positive, well, your delta T, it doesn't matter what it is because you're going to have negative minus, and this is going to be positive because it's going to be a positive and a positive. So you're going to be adding to your negative. So all is going to be negative, so spontaneous. Next, you're going to have negative delta H and negative delta S, which means you're going to be adding to this, and it doesn't matter what it is. So at a low delta T, you're going to have a negative delta G, which is going to be positive, and at a high delta G, high T temperature, a high T with a negative delta S, then this number is going to be very high, right? Which means you're going to be adding to it, so it will be positive. So that means that this is going to be non-spontaneous. So you have to figure out how these work. You have to like do this in your head and figure out how does this turn out positive with two negatives? How does it turn out positive? You got to figure that out. So let's take a look at an example here. All right. And here is the formula, the reaction. Carbon tetrachloride gas. And it's going to decompose into solid carbon plus 2 chloride molecules, gas. The delta H here is going to be equal to positive 95.7 kilojoules. And the delta S is going to be equal to positive 142.2 kilojoules. Joules per Kelvin. Sorry, joules per Kelvin. So that's my delta S. All right, so now what I want is to calculate my delta G at 25 degrees Celsius and whether it's spontaneous. So A, calculate delta G, right, at 25 degrees Celsius. And if it's spontaneous. Okay, so here we go. My delta G is equal to delta H minus T delta S. Okay, so delta G is equal to delta H. So plus 95.7 kilojoules. And then I need to convert this to joules because my delta G is going to be in joules. So I'm going to convert this, kilojoules, 10 to the third joules, minus, and now my T, which is going to be 298 Kelvin, times delta S, 142.2 joules. Okay, so my delta G is equal to 5.33 times 10 to the fourth joules, and it's positive, so the reaction is not spontaneous, non-spontaneous. Okay, so now, letter B, now that I know that, if it's not spontaneous, which it's not, determine the temperature it would need to be spontaneous. What temperature Okay, so in order for it to be spontaneous, I'm going to set my delta G to 0. So my delta G is going to be equal to 0, and then what I'm going to do is I'm going to say what I want is for that number to be larger than that number, so that my delta G actually turns negative. So I'm going to plug this in, and I'm going to say I'm going to set my 0 equals to my delta H, which is 9.57 times 10 to the 4th joules, right? That's my H, minus, and then I'm going to set my my T, which is my temperature, right? I'm going to set that to X, because that's what I want to know. X times 142.2. Now, and that's joules. Now, notice that my X, I want this to go negative so that it'll be spontaneous. So whatever my X is, I want that to be bigger. I want it to end up being bigger than that. Whatever my X ends up as, I want it to end up being bigger. So I'm going to solve for X. And when I do that, when I solve for X, right, so I get X is equal to 672.9 Kelvin. So therefore, my temperature needs to be greater than 673 Kelvin. At a temperature greater than that, my reaction will be spontaneous. So spontaneous above this. Above this temp. Okay, so now you should be able to do all the homework. All right, be creative, do your best, and tomorrow we'll talk about more about the next one. All right? Okay.